Good evening, everyone. My name is Claire and my colleague Emma, and our research is all about multi-threaded sparse learning for EEG signal translation to voice. And our keywords, we have the EEG is all about the recording of the electric field generated bastrophonic activity of a large group of neurons in a cerebral cortex. It's all about placing the electrodes on a subject's scalp. And the machine learning it enables a natural and seamless speech. And the multi-threaded is all about a multi-threaded approach that enhances the entire EEG to speech. Then the signal translation is all about converting the raw EEG signals into a meaningful form. Then the sparse learning is all about reducing the complexity of the model by selecting a subset of the most of the relevant features. And the voice conversion is all about translating one's voice to a more smooth voice without changing the linguistic content. Then we have the context of the presentation, introduction, related work, problem statement, research questions and objectives, the research contributions methodology, the dataset description results, conclusion, anticipated limitations and count actions, plan, then the references and the acknowledgement. Then the background, we have first of all, our topic is all about helping the impaired people, the speech impaired people, and the speech disorders profoundly of the life by impeding the social operations. So we have the EEG, which is all about what I explained in the beginning, and we have the machine learning, which I explained. So, and the related works, recent trends, and the literature review is all about. We have the multi-threaded sparse learning for EEG signal translation to voice, which is all about enabling the speech impaired people to communicate very well. And the recent advancements in the machine learning have shown promising results in voice conversion. And we have the voice scan which suggests a style transfer framework for VC based on the generative adversarial networks. And the CNN, these ones they're all about improving the accuracy of the speech recognition. And we have the voice translation combined with the linguistic information and is devised to extract the inherent characteristic in audio voices, which are sparse in benchmark databases. And we have the problem statement. And our research addresses the communication difficulty the speech impaired people face in everyday life. And the current speech assistive technologies are based on the physical inputs, such as typing, eye tracking. However, users with severe impairments, for example, the stammering people, the people on stroke, those methods that are available don't favor them. So, and our computation problem, we have collecting labeled EEG to the speech dataset is challenging, and unclear voices due to noisy environment, and signal processing and feature sparse learning for feature selection, mapping EEG features to speech, generating intelligible speech, and the real-time processing and deployment generalization across different users. And we have the research questions and objectives. We have the objectives to enhance the communication of speech impaired individuals, to implement an accurate and efficient signal-to-speech model, to ensure real-time processing and accessibility, to deploy the model a user-friendly platform. And the R search questions we have: how can ECG signals be effectively mapped to speech representations using machine learning techniques, and what are the most effective feature extraction methods for identifying relevant patterns in ECG signals for speech recognition. And the contributions we have: we developed an efficient signal to speech model, and we deployed, before that, we deployed an efficient signal to speech model, and we built the first advanced assistive communication technology. We developed a speech impairment model and enhancement real-time processing for practical use. And here we have the methodology. Here we have the flow diagram showing the methodology for the project, and it involves signal processing, feature extraction, machine learning, model development, speech synthesis and development. And the step up, we have the data collection and pre-processing. Data collection, we had a data set that consisted of voices for the sick and the healthy children. And the pre-processing, it involves cleaning and normalizing the audio data to ensure it is a suitable format for feature extraction. And it involves removing noise and background interference, and also normalizing the audio signal, understand the format. Then for the feature extraction and sparse learning, it involves extracting relevant features from the pre-processed audio data and transforming the audio signal to a more meaningful representation. And the sparse learning, it involves selecting a subset of the most relevant features to reduce the dimensionality of the data and improve model performance. And some of the feature extraction techniques we used, we had the MFCCS, the spectral features, we got the spectral centroid, then the model development, it has the signal to speech translation. And here, it is done by using the deep learning architecture, such as we use the CNN. Then we have the speech synthesis and output generation, model optimization and real-time deployment. Here, we refine the model to improve its performance and deploy it into a real-time testing. And after that, output is the predicted test. After outputting a test, the model will translate the test to a voice. Thank you.
So once again, hi everyone. This is Emmanuel Asimu, and you're working on a project which is multi-strategy sparse learning to signal translation to voice. So in our project, we are working on, we had data sets that had speech impaired people and those that had audios of people who are healthy. So in the data we collected data, we extracted features out of that given data, created models, various models, acoustic model, replace model, to translate the signal to speech. So we did a speech synthesis to generate an output. So there's an output which is a predetermined text. And then the model optimization and real-time deployment to deploy the model and develop it in the predicted text. So it would provide predicted text as you're going to see in the deployment process. So I'll proceed to, so now the data set description and extracted. So the data set description, as I previously told you, we had samples of healthy people and samples of sick people. So the healthy people had their own set of voices. These were voices of sick children, and the healthy people had their own set of data set, which was sick children. So we called the sample for sick children SLI and the sample for healthy. Healthy data set and the sick children's data set. So then the next we had EDA results, graphs and insights. So in the EDA results, graphs and insights, so we had to look at the audio data, analyze it, look at the patterns involved in the data. So we developed various kinds of graphs. These graphs included waveforms, histograms, spectrograms, and these graphs were able to show us the data imbalances and concentration of data so that we could be able to spot the different race patterns for the models we were to develop. Next, we had distribution graphs from the EDA analytics. So this distribution graph showed the one was histogram. So this was a distribution for healthy and SLI samples. So we had healthy children and SLI told you that data set for sick children in Labor data set. So in this data set for sick children, so we realized that there was a serious data imbalance because they had a data set of 2,000 and the SLI were up 2,000 samples and the healthy were up 1,000 samples. This was almost twice the SLI were twice the healthy people. So the healthy, the sick samples, the sick patient samples were twice the healthy patient samples. So this was a very serious data imbalance that we had to handle accordingly. So next was, this is a waveform for healthy patients. So we realized that the healthy patients had a voice concentration, their speech samples, and in the SLI samples, the concentration was outward, so upward. So these were the patterns we spotted in the EDA analytics. So the other sample we had a spectrocentrate. So we realized the green label was showing the SLI, the sick patients, and the blue label was showing the healthy patients. So in the healthy patients, we realized that there was a concentration of SLI samples because the voices were concentrated in a particular point, while there was a very wide distribution of the healthy sample. So the next is the zero crossing rate. So this was about the samples, the way they're crossing above the zero. And we had the distribution zero crossing rate. So this was also almost the same. So this data analytics helped us to identify the variability in our data, and we were able to develop models accordingly. The next slide. So here we developed different tables.
I'm presenting
Report for the logistic regression model. So in the classification report for the logistic regression model, we had a net zero or 97 decision, net plus or 0.9. Then the accuracy was 0.97. So here was the first try, and we had not included other things like sensitivity and consistency in the models. So the next was a random forest model. It had a precision for an accuracy of 0.60, precision of 0.43 in the net positive. This is was healthy, was 0.62. So we realized that our logistic regression model was our best model. Next was the SVM model, and the result was shown. And then you said classification report for the KNN model shown. So we realized that our logistic regression model outperformed all these models and was used as our best model to develop and deploy our application. So in the next slide, so we're going to talk about tables and highlight the insights. So still now we had a decision tree model. It was performing with an accuracy of 0.55. Then the gradient boosting model, we had its performance as 0.62. Then I also drew the distribution for a spectrocentrate by class for each sample, the healthy sample and the sick patient sample, the SLI sample. Then we also developed correlation matrices for all the models. Each model had its correlation matrices, but we picked out these few to represent the rest of the models. So I picked out one for the spectrocentrate, and then I recorded that. Then this was a spectrogram. So the spectrogram was showing the brightness, would show the bright colors and and dark colors for each of the samples, depending on the particular audio signal that is represented from the sample. Then next is, so we also had to develop, this is also a spectrometry for the SLI, the other one was for the healthy. To realize that there is a variety of there is variability in the brightness of the SLI speech spectrogram. Then we also developed a table to show the performance metrics for each model. So in the performance metrics for each model, we have the logics outperforming all the models, and the ADAPTS model ranking last in our models. So we did a randomness of 10 models, and the logistic regression model outperformed all of them. So this is a distribution graph for spectrometry. This is one of the confusion matrices. This was for the naive Bayes model, for the Gaussian model. Then this was a confusion matrix for our base model, which is the logistic regression model. It's actually the model that we deployed to our Hugging Face website. So then the conclusions and limitations. So in our conclusions, so realize that our project is a proposal to assist communication using machine learning. So if this project is successful, it will take a serious trend in AI, because this will research will focus on integrating other physiological signals and expanding vocabulary recognition and improving real-time performance. So in the limitations, we have accuracy and generalizations. Actually, we had many limitations. So there was background noise sensitivity in the samples, the limited language and accent support. So we only selected a few samples, and these were samples of 6 children. Then you had computational requirements, the requirements to develop the model, then the dependency and processing techniques, then the potential bias in the models. So the limitations are actually many. We only picked out but a few, but we are working with them to improve the sustainability and accuracy of our model. So these are our future works. So the model is to be scaled to aid security personnel, predict suspect voice patterns, and transfer them to text or voices that can be understood by the security personnel so that they can spot and whether the person committed a crime. So it's also going to be scaled to provide effective and rapid text in different languages. And this is going to improve word unity as communication is now effective. So we also believe that this model is, with the right data sets, advanced to the direction of telepathy and mind reading. This would help people communicate wirelessly and share text without involving typing, hence using their productivity. So we have, so next we have the acknowledgements. So we acknowledge our lecturer, 31 Women, who was such a useful person in this procedure. He guided us to develop the models actually from the start, even collecting data sets. And he directed us to handle the project and even deploying them. I also appreciate, acknowledge my colleagues, particularly the one I'm working with, and all the other colleagues in the machine learning class, who helped in times when a code was having issues, things were not working out. Thanks for lending helping hand.